All right, we're starting with a review of 1.1, so that we've talked about up until now. The first piece we talked about in 1.1 is this thing called matter, with a raised hand. How would you define it? I got only one hand. I would expect all your hands to be up. How would you relax? Relax. This is a way for me to see. Do you know? How do you define matter? Right? All right, Etienne's going to burst if I don't ask.
That takes up space.
Space and mass. Okay? So those two pieces. Takes up space and has mass. Okay? We talked about the two main parts of matter, the two main categories, that you have pure substances and you have mixtures. Okay? And I ask you again with a raised hand, what's the difference between these two things? Pure substances and mixtures. Two hands? Hang on, relax. This is a way for me to see who knows. All right? Give you a moment to think. I'm not going to zip so fast through this as you can't think about it. Mixtures, pure substances. What do you think, Shelly? Which is? Mixture. Mixture is a combination of two or more substances and two or more pure substances, right? That we've mixed together. Don't answer out loud, please. When I make a mixture, is it a physical change or is it a chemical change? Don't answer out loud. Physical change or chemical change? Let's do a hand vote. Is it a chemical change? Please raise your hand. Okay? A mixture. Is it a physical change? Please raise your hand. Why? Why is it a physical change? Because you're correct. It is a physical change. Why? Why is it, sir?
Because when the mixture comes in, there's no chemicals involved where it's changing where a new substance is going to become.
Beautiful. It stays what it was, right? There's no change in its properties. We are just simply occupying the same space. Sure, right, that Neapolitan ice cream, right? We're mixing them together, but it's still chocolate and vanilla and strawberry, right? Exactly. All right? So this would be a physical change, right? Between this would be a physical change. Okay? So a mixture could also become, a pure substance could also become a compound. And I ask you, how does a pure substance become a compound? Because a compound is a form of pure substance. So I'm curious to hear what you say. I like the hands. That's what I'm looking for. I promise. I want to see what you're doing. I want to give folks a chance to think. So it's not a matter of who raises their hand first. Got some questions? Got some thoughts? How does a pure substance become a compound? Or maybe, why is a pure substance a compound? What do you think, Wes? There's a chemical bond, okay? Anyone want to expand more on that? You're exactly correct, sir. What else? Sir? It is definitely a chemical change that happens to these pure substances. Yeah, it becomes a totally new something, right? That's what this chemical change happens. Totally new, but unique, but pure, right? In order to break it back into its elements, we would have to take it and perform some other chemical change on it. Okay? Elements, of course, being the most pure substance, right? A pure substance at its simplest. Okay, and then in mixtures, of course, we have the two. We have homogeneous and we have heterogeneous. Homogeneous meaning the same throughout, right? Heterogeneous meaning different. So that Neapolitan ice cream, different. Mixing it all together, that nice kind of reddish, brownish, gooey, yeah, that's a nice, beautiful homogeneous mixture.
What would be an example? What would it be like?
Now, your textbook, if you looked at that little diagram that we talked about, it's there on page 24. They give you some examples of heterogeneous and homogeneous. Yep, those are heterogeneous. Homogeneous, things like soda, gasoline, and air. Okay? I think about when you see the digger, front loader that's digging down, and you see that there are those layers of dirt as you dig down through it. Yeah, exactly. And also, like if you were to have a bucket full of dirt, it's not the same. You know, it's different. They've got little rocks. You've got little white things. You've got right. So it's different. It's good. Little fertilizer. You think about like topsoil. You're talking about. Yeah, it's good stuff. Okay. Questions there? These are our big pieces from 1.1. Oh, absolutely, certainly, yes.
Are you the type who tries to like put trick questions?
No. I'm telling you what you need to know. I'm recording all of this, so you can come onto YouTube later and you can.
That's all we need to know for Jeff.
No. We'll talk much more about it. I'm reviewing. Thank you. All right. So we're going to jump into 1.2. And what I want to start off with are physical properties. That's what we'll start with. Physical properties. I'm asking you, first of all, what are they? What are, not like naming individual ones, but how would you define physical properties? Got 2 hands. Okay, look for hands here. Got a few hands. I like it. All right, Griffin, what do you think? Oh, nice. So it's not changing the actual substance. Okay, that's like when we're performing a physical change. He's saying. Okay, I like that. Other explanations. Maybe some more details. What do you think, sir?
It's not changing the composition.
Okay, good. And so I can observe these things without changing them. Okay, sir? Oh, so these are examples. Absolutely. Yeah, observable without changing them, without putting them through some sort of chemical reaction, right? Because chemical properties, that's how we see them. We have to put them through this chemical reaction to see these chemical properties. What's something to add? Absolutely. They are still what they are. We're not changing their structure or their identity.
Like salt water?
What do you mean?
Like if you're dumping salt in water, you're not.
Sure, right. We're just mixing the two together. Yes, no chemical change. Definitely. So I heard someone say color was a physical property. Let's name some others. And give me one of these guys. Okay, give me one of these guys. Alex, you said what, sir? Luster. This is a great chemistry word. Can anyone define for me what luster means? Hang on. Anyone know what luster means? It's a great chemistry word. Sir? What do it mean, sir? Shiny. Yeah. It's a fancy way of saying shiny. Absolutely. Okay. Another property, sir? Sorry? Cleavage. What do you mean by that?
It's the lines that splits when you like cut a rock or something, or a diamond.
Okay.
How solid it is.
I'm with you. So solid, but I'm gonna. Oh boy, didn't spell. How about we say, instead of saying solid, what if we were to say state of matter? A state of matter. Now this is one that folks are always a little sketchy on. So let's take a good friend water. Okay? I take an ice cube out of the freezer, put it in my hand. It melts, right? Eventually. And changes into water, right? I take that water, I put it in a pan, right? And I boil it, and the water changes to what? Steam, right? It's gas. So if we got solid, we got liquid, we got gas, right? Yeah, plasma is a very tough one for us to do with water. Okay?
What can you make into plasma? Or make plasma cube?
Plasma is just simply an ionized gas. It's a gas that has a charge to it.
Can we freeze plasma?
Yes.
Make plasma cubes? So is it a state of matter or not?
It is. It's like the fourth state. But it's very rare. You need like very high pressure situations or special kind of things. Yes.
Big ice head. Big ice plasma.
No, you can't. You can't. No, not that I'm aware of. Not that I'm aware of. So, again, we've changed this water, right? It's gone from ice to liquid to gas. But has it undergone any chemical changes? It's still H2O, right? Its structure is unchanged. We've just allowed the molecules the ability to move more. We'll talk more about that in the future. So therefore, changes of state, going from a liquid to a solid or a gas to a liquid or any of those, that's a physical change. A physical property would be whether it's a solid or a liquid or a gas. Okay? Easy one folks commonly miss on the test. So I want to make sure you're comfortable there. Other physical properties. We've got a whole bunch more of them. I'm curious. What else you got, sir? Smell. Sure. Yeah. Sir?
Hardness.
Sure. You could say it's hardness. And I was trying to figure out how to put cleavage, but I think that would kind of come in this. Because that cleavage is just like where you're actually taking it and breaking it along these certain lines of weakness. So I would kind of put it with that hardness kind of category. What do you think? Density. We'll talk about that one in just a moment. But that's a beautiful one. Density. Okay, sir. Sure. Melting or boiling point. Because again, that's what changes the states of matter, right? What do you think, Scott? Sure, absolutely. Freezing point. Beautiful. What do you got, Corey? It's what? Tell me. Oh, like it's. Oh, I got you. I'm trying to think. How about appearance? Which being slightly different than color. Yes. Sorry, I didn't know where you're going with street there. Yes. It's visual. What do you mean? Sure, right. Absolutely. How it looks. Beautiful. Beautiful. I like that. So, can you see that these are things we can observe with our, senses, right? I suppose you could bang it on something and see how it sounds, but not really the easiest of properties.
For appearance?
Yes.
Could you also say how it feels?
Sure. You could talk about its texture. Remember some of these we were doing with our lab we did the last 2 days, right? We were talking about the characteristics, the properties you observed. You were observing these physical properties. Beautiful. The difference when I add in chemical properties, and chemical properties are over on page 38. No, they're separate. Okay, but again, it doesn't change what it actually is, though. You're correct.
You can't observe it without putting it through a change.
But it's not, all it is just changing temperature. It's not actually changing the structure of the substance. You're right, because again, this is where folks get confused.
I mean, it kind of is. I mean, the atoms get rearranged.
No, well, they just move around more. That's really all they do. But it's not actually, in other words, it's not taking it from one substance to another substance. It's still H2O. Okay, it's good. I like the way you're thinking. I like the way you're thinking. So a chemical property is something I can only see when it reacts. Okay? So one of the big chemical properties is how does it react with oxygen? So we can see, does it react? Does it not? Is it flammable? Is it not? These kind of things. There's some examples there on page 39. You can see some examples of these reactions that are occurring. In the first one on the top there, you've got bromine that's reacting with aluminum.
Can we please do that experiment?
We'll do some more. Don't worry. The second one down, you've got oxygen that is reacting with iron to form rust. This is just rusting that's happening very rapidly in this pure oxygen environment. You've got water that's being broken apart into its hydrogen and oxygen pieces. We'll do this one together. We're breaking this apart. And then on the bottom here, we are showing, I think that's hydrogen peroxide. That, you know, you have to leave. Have you ever seen these hydrogen peroxide containers? That they're dark. They're like this brown plastic. Yeah, because the sun will help break it down. And if you leave in the sunshine, it becomes just water. The oxygen all escapes. Because it's H2O2. That's the formula for hydrogen peroxide. So these are chemical properties, chemical changes that you can see. You have to react them. You can't just observe them. You have to form a reaction. We have to change what they are to visualize these chemical properties. Okay? I'm not sure I understand. Yeah, you can react just about anything together. It just depends on how reactive they are, whether they actually do much. Sure, right, acid will eat your skin. Yeah, definitely. It'll react. Let's not. Yeah, we will. Absolutely. All right. Let's take a pause here. All right. One of these properties, one of the properties you talked about was density. This is what our lab is going to be about. So let's talk about what is density made up of. There are two pieces that we need to know in order to find the density of something. Okay, give me these, because I want to see before you just holler it out. I got 3, I got 4, 5. Just finding it on the page is good because it's there. We read this, right? It's there. All right, Chantel, what you got? Well, sure. The two pieces. What is it made of? Beautiful. So the actual textual definition is the amount of mass contained in a unit of volume. Okay, let's try to say that in English. It means how much mass do you have in how much space? Okay? If you wanted a formula for it, density is what? How would you find density? Mass, what? Divided by volume. Okay? If we had to talk about units, grams over milliliters. It could also be grams over cubic centimeters. A milliliter and a cubic centimeter are the same thing. They mean the same amount of volume. Why we use one over the other, I don't know. Yeah, usually area, you use cubic centimeters. You're correct. Okay? So the lab that we're going to be working at, which is over here on page 36 and 37, is talking about pennies. Pennies have a copper shell on them and currently are made of nickel on the inside. But in the past, they used to be made out of something different. And, I'm sorry? It was at one point, yes. But now we just have a little copper shell. Does anyone know why do we do that? Why are they not copper through and through? Because why? Copper is expensive. Like people will go in to new homes as they're being built or old homes as they are abandoned and literally cut out the copper pipes and sell the pipes. Sure, right. It happens. Because again, copper is valuable. So therefore, even now, even with using nickel, pennies are still worth, like it costs more to make a penny than a penny is worth. It costs about 3 cents to make a 1 cent. Right. It's because we're American, brother. We don't back down. We go into debt. Right? It's good. All right. Maybe. They've been talking about that for 20 years, but maybe. All right, moving you on. We're moving you on. So there was actually a year that we'll see if we can't find where the composition of penny changed. What the penny was made out of changed. And therefore, the density of these pennies changed. In the lab, we're going to see if we can't determine when was that. What year was it that this occurred? Okay? Should be fun. Let's check out in your textbook, because density is a very important physical characteristic. Go to page 850, would you please? In the back of your textbook, page 850. I want you to see something. 850, yep. And it continues all the way through 854. This lists you all these properties of elements. All these different properties of them. And can you see right about in the middle of that column?
Copper.
The density
Interesting. Here's just, this one right here.
is void. There's nothing there.
Well, it's because it's only an element that sticks around for a tiny bit of time. But you can see density is listed there, right? This is one of the ways that we differentiate elements is based on its density. It's a very easy way to differentiate them. Because all I need to do is be able to weigh them, find their mass, right? And see how much volume it takes up. Okay? We'll learn many more. You'll learn all about these different properties. What their melting points are, atomic number, atomic mass, specific heat. That's the simple equation. Yep. Find the mass, divide it by the volume, you get its density. Yes? Derivative? What is that?
Why is there like
Oh, like where did it come from? Like how?
that are just there and they have nothing?
I'm sorry, I don't know that. I don't. I'm sorry.
Like even California has some stuff.
Yes. Some of these elements you're looking at are only around for the briefest of moments.
That's where this just
Right.
is real.
Yes. Sorry?
There's 5 in a row and they have no
Sure.
thing.
Yeah, that's a lot of these guys on the bottom of the PT.
Yeah, but California has like the melting point and radius, and these ones have nothing.
Yeah. Again, what you'll see is there are a number of elements that how they make them is they take and they smash other elements together. And so there's literally only a few atoms of these things formed. But they can repeat it enough that they know, yes, something is there. But it doesn't stick around long enough for us to really find out all about it.
Isn't there ones where like we know there's an element there, but we just haven't discovered it yet?
Now, there's only a couple of those in the very bottom right corner of the PT.
That's what I'm talking about.
No, I don't think those are listed there.
Unum, hexene.
Oh, okay, maybe they are. I'm sorry. I wasn't sure which ones you were looking at. Yes. Yes, you are correct.
Yeah, so
Yes.
we know they exist. We just haven't.
Right. Yes. Okay. Last but not least. 35, right? We're doing good. We're doing good. Law of conservation of mass or matter. You with me? Yes, sir. Okay. Can anybody give me a definition? What does this mean when we say the law of conservation of matter, law of conservation of mass? What do you think, madam? Not created nor destroyed. So in other words, if I'm doing an experiment, however much I start with, I have to end with. Realizing I got to make sure I capture any gas that escapes. I got to make sure it's an enclosed reaction. But the mass will not change. Okay? I have a hard time believing this sometimes when I'm on the golf course because I swear that matter is destroyed as I lose the ball in the woods because I cannot find it. It drives me crazy. I swear it must be destroyed. Or maybe I just hit it so hard with my...
It goes in like a pond, but it's like it's deep enough so that fingers out getting in. It's just
I got you. Yes. Well, they have these big long reacher things you can reach in there and get them with.
Yeah, but it was too far out.
Ah, well.
I could like actually step in
You could. You could. And the crocodile comes and you lose a leg. So, law of conservation of matter. Are you with me, friends? However much I start with, I have to end with. For our reactions that we're going to talk about, this will be a key point. If I have 20 carbon atoms I start with, I must end up with 20 carbon atoms in the end. They can rearrange. They can go in different compounds and different groups, but there must be the same from what I start with to what I end with. Yes, we'd have to encapsulate and contain all the air. You would just kind of change its form.
But what if I blow it up outside?
Doesn't matter. We'd have to contain it. In other words, if you let it escape, you're going to lose mass. But if you contain it all, if it's an enclosed setting, no matter what you do to it, you cannot destroy the matter.
But then, okay, we can't destroy the matter. All right, that's the.
You can destroy the table, sure, but you just make it into smaller pieces. That's all.
Not going to have the same matter.
No, it will. All of that contained.
But if it's not contained, how does this law make sense?
Right, then it just escapes in the atmosphere. You haven't destroyed it, you just lost it.
So I can blow it up. I know I can't destroy the matter,
Yes.
but it's still going to have the same.
If you take all of those pieces that you blew up and you put them back together in one area, not to make a table, you couldn't do that. But if you combine them all into one enclosed space, it would weigh the same as this table. Yes. It would not look nice. You would not be able to write on it. Yes. Yes, sir. Shh, 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 shh. If you burn it, it's fantastic. He says, what if I burn this thing? Again, if I burn it and I capture all the gases, because basically you're just taking it from a solid usually and changing it into some sort of a gas, but it still has the same mass. It's a great question. Because you think about burning means things go away. It doesn't. It just changes form. Just changes form. Well, if those existed, it would just change positions on the time graph. It wouldn't actually change its matter or its mass. Okay? So this is a key point. Yes, sir.
So with the universe constantly expanding,
Right.
does that mean that we need more matter? If it's a law of conservation of matter, is there more matter being made, or is it just more matter?
No. At one point, it was all contained in this small, tiny spot. This is the thought about of the Big Bang. And then it has expanded since then. Would I have any problem at all with that expansion being the result of a creation? I don't have no problem with that. You know what I mean? Maybe just from God speaking it started and then it expanded. I have no problem with that. Billions of years? Well, again, there's some ways you can talk about that. Okay, we'll talk about these things. Because that's just simply, if you take the rate it's expanding and you rewind it, that's how they get that number. Okay? Has it always been expanding at that same rate? Maybe not. Okay? Are you with me? Any questions here? Pretty straightforward, I think. Right? Good. Your assignment. I wanted to show you this. This is on Schoology. This is the class page. Hopefully you've noticed this over on the side, telling you what's coming up. These guys are assignments. These guys are assessments. Okay? So that way you have an idea of what's coming. The assignment for tomorrow, of course, your lab report is due. But also I'm asking you to do the questions at the end. Again, please don't shuffle on me. Let me finish. So have a seat, and then we'll be done. On page 42, numbers 6 through 9. This is to help you practice using these physical and chemical properties, physical and chemical changes, reinforcing what we did today in class. Okay? Your lab can be either turned in on Schoology, or you can bring me a hard copy tomorrow, either way. Okay? Any questions that you have for me? Make sure you do read that lab as well. Okay, the density lab, pennies. That was on 36, I think. Okay? Good. I will even wait until this clock says 34, and I will dismiss you.